It was fun. I've never done anything like this before, actually. I think the idea is really, really cool, actually. I wish someone would have come up with an idea like this when I was an undergrad.
Hello everyone. Welcome to another chapter of the series of interviews conducted by the Department of Chemistry, University of Colombo. My name is Chathuri Rajaratna and I am here with two of my colleagues, Madhav Pereira and Chatushka Devindi.
Hello, I am Madhav.
Hello, I am Chatushka.
We all are final year undergraduate students. Today we will be interviewing Professor Maria Abrahamsson in this session.
Professor Maria is a professor in physical chemistry at the Department of Chemical and Biological Engineering at Chalmers University of Technology in Sweden. She was promoted to an associate professor in physical chemistry 2015 and professor in physical chemistry in 2020. Currently, she is the director of the area of advanced materials science at Chalmers.
She is interested in the areas of photophysics, photochemistry, photocatalysis, laser spectroscopy, molecular systems, heterogeneous systems, and nano-crystalline semiconductors. We are going to talk about her broader scientific career and her past, present, and future as scientist. Good morning, Professor.
Good morning.
We warmly welcome you to the interview and thank you for giving us your precious time out of your busy schedule. First and foremost, Professor, may I take you back to your childhood? What was your early inspiration to become a scientist?
Back to my childhood. It's hard to pinpoint a specific point that made me want to become a scientist. When I was a kid, I was interested in many different things, and I had plans to become a reporter, and I had plans to become a teacher, and I had plans to become lots of other things. But I think in the long run, I was interested in solving problems, and it turned out that science was great for that. So it was sort of not a straight paved way to the career as a scientist, but that's where I ended up, and I'm very happy with it.
It's also inspired me. Why did you prefer science over the other subject streams like politics or economics?
I'd never been particularly interested in economics, but I am actually also very interested in politics and in policy making. So I actually think that politics would be better if more scientists were also involved there. But that was also, I think, and as I said, I'm interested in solving problems. And politics is also a good part of solving problems. So, and in some ways, I am interested in both. How it ended up being science, I don't know who can resist looking at electron transfer reactions. But I am interested in both. And when I made the decision, it's like when I did my undergrad studies, I studied chemistry, I studied geology, I also studied ethics, and a little bit of economics, actually. So it's like I've done a little bit of everything, but somehow I just ended up in science.
Professor, could you briefly describe what type of research you are conducting these days?
So I would briefly describe it as that we're looking at photophysical and photochemical processes in molecules and materials that are relevant to solar energy conversion. And in a little more detail, we mainly use optical spectroscopy techniques to study this. But we also, work with larger catalytic setups and things like that. So
what is the Abrahamsson Research Group and what kind of specialty does it carry?
So the group is a diverse crowd. Currently, we have people from Sweden, from the United States, from from Brazil, from Spain, and we also have someone from the UK joining in January. So it's a diverse crowd, and what we're good at is it's mainly optical spectroscopy. That's our core expertise, but also the transforming of in our case then solar energy into a fuel or electricity, but we're also very interested in fundamental photophysical properties. I don't know if you expected a different answer to this question, maybe.
Maria, it is excellent. In terms of your expertise, could you explain what is a photocatalyst and how it is involved in the generation of solar fuel?
So, I guess almost everyone has an idea what a catalyst is, right? It's something that makes a reaction go faster without being consumed itself. So in theory, a photocatalyst is just something that is activated by light. In practice, a lot of the photocatalysts we work with are not actually fulfilling the requirement of not being, consumed themselves, because they have a little tendency to degrade over time. And also the systems we're working with, typically we use a photosensitizer and a catalyst together. So it's really the photosensitizer that sensibilizes the catalyst to the light. Because it turns out that it's very hard to get both the catalytic functionality and the photosensibility into the same molecule and make them still be stable.
Okay, amazing. Professor, the aim of your upcoming research on photocontrol catalysis is to find a way to control yields, rates, and mechanisms of multi-electron transfer reactions in photocatalytically active hybrid materials. So can you explain about it a little bit?
I can try. So this is actually a completely new project. We haven't even started it yet. We got the funding the funding decision just a few weeks ago. But so in short, the idea is that a molecule has many different energy levels. So we have translational energy, we have rotational energy, we have vibrational energy, and electronic energy. And especially between electronic levels and vibronic levels, there is some coupling. So, they affect each other. And a few years ago, there was a very nice paper by Julia Weinstein in Sheffield, there they showed that by, when you do a photo excitation, you send in one pulse of light, and then your reaction is happening in the excited state, or at least it starts out in the excited state. And what they could show was that giving not one pulse of light, but two, they could control which pathway this reaction took, because they managed to deactivate one possible route for the electron to take. So that is sort of the inspiration for this, that we should be able to build molecules and materials where we can design, and control which pathway it's taking by giving more than one pulse of light. Whether we will succeed, we will see. I think this is going to be a very hard but very, very interesting project. And, especially since what we want to do, if we're ever going to be able to do solar fuels, we need to transfer quite a few electrons. It's not just one electron transfer, it's more than that. And that always becomes complicated because of charge stabilization and whatnot. So.
Yeah. I would like to ask, what other academic subjects have you been interested in the field of science, and why?
So obviously, chemistry. I am a chemist by training. So that's always fascinated me, how you can make new molecules, but also how you can understand how they interact with each other, and how you can make them do what you want. I guess that's why I am a physical chemist. I also studied a lot of analytical chemistry, just because being able to measure things is useful, right? And as I mentioned earlier, I also studied geology, actually, which also came from sort of an interest in environmental matters. And also, you know, because it's fun when you're outdoors and just be able to see that, oh, this has to be this kind of rock, etc. And I've also studied a little bit of economics, just for the fun of it.
They are really interesting. As you are a professor in physical chemistry, can you explain how physics concepts relate to chemical systems?
So this is actually a very hard question, you know, because as you said, I'm a professor of physical chemistry. I actually did my graduate work at a division of chemical physics, and still we were mostly chemists working there. And still I'm surrounded by mostly chemists, but we have a neighboring division at Chalmers that is called chemical physics, and there most people are physicists by training. And there is a lot of overlap in what we do. But what I have found over the years is that chemists and physicists have slightly different language, slightly because we have different undergraduate training. But in terms of research interests, I would say very much overlap. And you know, it's the same of like it's not really clear cut and necessarily where the border between chemistry and biology is either. If you're, you know, or for that matter, biology and physics. There's biophysics, there's biochemistry, there's chemical biology. And I think it's hard to pinpoint exactly. And I think it's good that we are collaborating more because we understand more of the world that way.
Professor, your recent publication is about singlet fission related research. Can you please give us a small introduction about singlet fission?
I can try. So singlet fission is essentially a phenomenon that's been known for many decades now, and that had a little bit of interest back in the 1900s, and then around 2006 maybe it saw a revival. So what the whole concept is if you take it to the easiest level, is you take one photon and you manage to divide that one photon into two triplet excited states, so that you could, in principle, extract two charge carriers from it. So essentially, it would be a 2-for-1 process if you talk leeway language. So of course, this is not. It sounds easy. It turns out that it's not. There are lots of energetic requirements that needs to be fulfilled. So there are very few molecules that can do this. And it's also, all the molecules involved in this have to be typically like organized in a very specific way to be able to interact the way they need to, and also to not undergo any detrimental processes if the singlet fission happen. So.
Professor, on the other hand, there are many molecules that show singlet fission like pentacene, tetracene, anthracene, etc. Why did you choose diphenylisobenzofuran in your research?
Very good question. So there are actually several reasons behind this, and one of them is that is also a molecule that has been predicted to undergo singlet fission. So that's of course one of the reasons. As I said, there are energy requirements that need to be fulfilled, so you can't just take any molecule. So that was one of the reasons. One of the other reasons was that we wanted to investigate this on surfaces. And my organic chemistry collaborators predicted that it would be fairly easy to modify this molecule without disturbing the electronic properties, so that you could attach it to a surface. And as it turned out, it was fairly easy to put on the linker, but it was also sort of hard to make this molecule stable. So It was a very fun project, but it was also involved a lot of effort in making everything work and a lot of glove box work.
Superb. This is my next question, Professor. As we see the current situation of the world get worse day by day, it seems that nature is trying to convey a message to be eco-friendly for further survival as human beings. So what kind of strategies your research group follow in order to ensure that a minimum harm is caused to the environment?
So, I would say in one way, doing research by itself is not necessarily always an environmentally friendly activity. We sometimes spend a lot of energy and materials in doing things that didn't work out for the greater good, because we are looking for something where it will work out. For example, I mean, we're trying to work with materials that can convert solar energy into either electricity or fuels, and we try to do that with benign materials that we have a lot of, that are cheap, that are non-toxic, etc. But there are no guarantees, so we always have to challenge ourselves and ask ourselves, are we doing the right thing? And do we think that this is going to be viable? And I think that's the best thing we can do. And then, of course, we try to avoid things that we know are not good for the environment.
Perfect. And I would like to know whether you have any targets to improve the existing technology in the field of science that you are interested in.
That's an interesting question. I mean, we mostly do very fundamental research in my research group. So, we really study the fundamental energy and electron transfer processes, what happens when the light interacts with the matter. And, of course, we hope that if we can understand that, we can help, building better solar cells, or actually create functioning solar fuel devices, etc. But I would say that I'm more interested in the fundamental research than in applications and doing inventions.
Professor, how do you make the public aware of the latest scientific discoveries that are happening?
So this has been a strange year for these kinds of activities, obviously, because in a normal year, I typically say yes to, giving public lectures or being part of science festivals and whatnot, because I think it's incredibly fun to talk to people in person and being able to explain my science and show some experiments and whatnot. And since the pandemic hit, of course, we haven't been doing a whole lot of those things. So we've been trying some other things. This was actually not this year, but I did a podcast about my research a few years ago. That was only one episode, but it was still fun and very hard, actually, because you essentially talk to yourself, so it's hard to know exactly what level you should put that on and who will listen to it. But so that's public lectures when I get a chance, things like podcasts or whatnot, popular science lectures, science festivals.
Those seems very helpful for the public. Would you like to share the hardest part of your career as a professor?
Oh, the hardest part of my career. It's a very interesting question. I think if we start with the easy part, the very best and easiest part of my career in one way was actually doing the postdoc, not because it was easy per se, but because that's the time in your career when you get to focus on research only. As a PhD student, you need to finish your thesis. You should also do teaching. You need to figure out what you do next, etc. which is all fun, but can be a little stressful sometimes. And then when I went away for my postdoc, I was in the US. I came there and I decided that for the first year here, I will not think about my future career whatsoever. I will just do science. I will just enjoy it, which was lovely. And I think the hardest part might have been the transition, actually, from assistant professor to associate professor, or not the transition itself, but the work that took. It's like when you're trying to find like your own line of research and how does this fit into what everybody else does. How do I find my niche? How do I get funding for it? But I think all stages has their ups and downs. But in a way, I think that was I was very lucky in the beginning of my assistant professorship and got substantial amounts of funding then. And then I couldn't really keep that up when I came to the transition. So that was a little bit hard, but it also takes time. And now things are working out well again. So.
Great. I have read about graphene flagship, one of Europe's largest scientific projects conducted by Chalmers University of Technology. What is it and how is it helpful in the future of the technology?
Oh, great question. So the flagships there are a few of them, and these are really, really large efforts funded by the European Union. So there is one about the graphene, there is one, I think, about the brain, and there is one more that I can't think of right now. So, and what's fun with these flagships is that they really combine really low technology readiness levels, so what we would call, normal research, all the way to innovation and commercialization and whatnot. So the flagship has its coordinator at Chalmers. So there is a person who is very well known in that field and who is trying to coordinate all of these efforts all over Europe, which I imagine is a challenge, probably a fun one, but I'm sure it's a challenge. And part of this is, of course, to be able to bring out the graphene and also our 2D materials into applications for, whatever it may be, packaging, energy, or, composites, making lighter materials, or electronics for that matter.
Professor, my next question is, what is Horizon 2020? Is it helping scientists all around the world?
So Horizon 2020 is what's called a European Framework Program. Excuse me. That funded research within, or mostly within, the European Union between 2014 and 2020. So now they're launching a new framework program that is called Horizon Europe, that will go on between 2021 and 2027. So these are really large efforts in terms of funding, but it also, covers many different areas, many different aspects, and mostly is focused on research done within the European Union, but there is also, some grants for traveling or for incoming people. So I think you could say that it hopefully helps people around the world, but there is definitely a focus on the European Union.
Professor, you received your PhD in physical chemistry from the University of Uppsala in 2006. What were the challenges you faced when you were developing as a young scientist, and how did you overcome them? Can Professor elaborate on this question more?
So challenges as a young scientist, there are many. Time is one of them. Of course, you always want to do more when you actually have time for it. Another one that I think was not always easy at the time is, to figure out what is your path here. How do you make your science, interesting, but also how do you make it yours? How do you define what is your project? It's great to have collaborations that really help science. You have someone to talk to. You generate ideas together. Makes everything much better. But it can also sometimes be hard as young scientists, knowing exactly what is your way here, so that you actually are helping steer the project and not just rely on your collaborators. And that is, of course, partly a matter of self-confidence. Sometimes you meet people who are very confident in their opinions and they think they know everything. And if you yourself are not as self-confident, that can be hard to navigate, I think. And also I think a lot of young scientists struggle with imposter syndrome. So they wonder, is what I'm doing good enough? Am I good enough? And that, I think, unfortunately, I think that's incredibly common among young scientists. So what we actually do in my research group is that we work a little bit on trying to really compare, not necessarily our work, but like we read papers in a journal club, and it's like, what is it that really is the key point here? Why made this work? Why did this work make it into JAX, or why did this work make it into Nature, etc.? Trying to understand that so that we get the keys to really judge our science, and so that we can focus on the right things instead of asking ourselves, are we good enough?
They are really inspiring. What kind of advice can you give as a professor to a student who pursues science and research as a career?
Oh, I think the best advice I can give is that you should do things that you think are fun. There are never any guarantee for success, but if you do things you think are fun or find interesting, at least you will probably have learned something, and that, I think, in itself is worth something. So if you have fun, if you learn new things, you haven't wasted time, even if it didn't work out the way you wanted it to.
According to your opinion, what kind of a field should we focus more on for the advancement of science and technology in the near future?
Oh, well, I think there are many things we should focus on. And when I say we, I do mean the scientific community as a whole. But yeah, I think it's pretty obvious these days that we need to understand more about viruses and other microorganisms. I do think that the climate issue is one that we really need to handle in one way. So renewable energy and climate friendly activities in general. But I also think that, it's like 1.5 years ago, no one had an idea that all we would be talking about these days is a pandemic. So I also think that there are some things that we cannot predict whatsoever. And therefore, I think it's really, really important that we allow people to do what can sometimes seem as obsolete research that is not of great interest to anyone except a very small community, because who knows when we will need it. If people hadn't been doing fundamental research, we would not have vaccines being distributed now, just a year or a little over a year into this pandemic. So I think it's, it might be good to focus on some things like, climates or virology or things like that, but we also need the just curiosity-driven research.
I think we have come to the end of the session. So finally, I would like to ask you, as a budding scientist, what is your take-home message to students who have lost their curiosity and thinking power in the digitalized world?
Oh, interesting question. So I think what I would say is read fiction, not on a screen, but in an actual book. Of course, people are different, but for me, I think reading fiction it's actually a great way of generating ideas, because it puts my mind in, I get to take part of someone else's idea of the world, or walk into a different story, and that sort of, yeah, for me it works. Like I can generate science ideas while reading fiction about something completely different. And it's also very nice to, read on paper instead of on a screen. So that and getting out in nature and get fresh air, that would be my 2 pieces of advice.
Yes. With that, the time has come to wind up the interview. It's an amazing discussion. Words are powerless to express our gratitude to you, Professor. We truly appreciate you and your valuable time given for us. Your knowledge and leadership provides us with a priceless model for our own careers. We thank you from the bottom of our heart, and we consider this as a golden opportunity we got in our undergraduate life.
Professor, thank you very much again. This concludes today's interview with Professor Maria Abrahamsson of Chalmers University of Technology, Department of Chemical and Biological Engineering. We really appreciate she was able to allocate her precious time to share her thoughts.
I hope this interview will be very useful for young emerging scientists to become multidisciplinary experts of their field of science. And thank you everyone for joining us today. Stay tuned with us to have more exciting interviews with eminent scientists all around the world.
Thanks, it was fun. I've never done anything like this before, actually. I think the idea is really, really cool, actually. I wish someone would have come up with an idea like this when I was an undergrad.